So let's start with something for our meter stick. There we go. And we're using this to replace the bridge from yesterday. So I guess I should probably put this on the screen. Yay. So you should expect better. You really should. There we go. There's a meter stick, and I think we'll have some upward forces acting on it. So one here and one over there. Does that look good? So are we good to say TL and TR? Okay. So the meter stick has weight, and I'm just going to, oh my. Perhaps we could get that sucker in line a little bit. There we go. Wow, that was quite scandalous. So we'll put that there in the middle, and something like that. And we're thinking this. We know what this one has to be, right? Because this is going to be 0.78 newtons. It's the weight of the meter stick. Still seems a little hefty for the compared to the other two, but this is what we got. Whatever. So now we're placing it's 500 grams. So I think we should multiply by 9.8 because this is a lab. So 4.9 newtons. And we're placing that at you said the 40 centimeter mark? All righty. Oh, wait, no, 40 is going to be, no, that's about right. Oh, that's not right. So 47 centimeter mark. We know it's greater, so something like that. There we go. And this will be 4.9 newtons. And just to keep everything together, 24 centimeters, 40 centimeters, 50 centimeters, and 76 centimeters. That's all the different locations?
Mr. Shelton?
Yes.
Would it make a big difference if it's 0.78 newtons instead of 0.76 newtons?
I don't think so. I mean, was it 0.76? I thought it was 0.38 and 0.38. Oh, no, sorry. Was it 0.39 and 0.39?
Yeah.
Isn't 0.39 and 0.39 0.78? I mean, it was changing behind my back. I was looking at you guys.
I saw 0.38 first, so.
Okay, so if you guys want to change it, I mean, we're talking 100th place, so we're probably okay. But, all right. So, just a reminder, we are doing a statics problem. We're trying to figure out what the two tensions are going to be in the string holding the meter stick. And again, it's like a bridge problem. So we start out knowing that net force has to be 0. That's what makes it a statics problem. And unlike the other free body diagrams we've drawn, this is still a free body diagram. The difference is that no longer do we have it associated with just a point, because we know the point of application of these forces also matters. So we have two upward forces, TL and TR, and two downwards forces, 0.78 newtons and 4.9 newtons, but they have to sum to be equal to 0. Suggesting that TL plus TR is going to sum to be equal to 5.77 newtons. Is my arithmetic correct? All right. So again, we can't solve for TL or TR directly here because we have two unknowns and only one relationship. Net torque is going to allow us to generate another relationship. That's all it is. It's just like another net force equation. There's more to it because it's more of a weighted average. Yeah?
It's 5.68.
Okay. Being wrong is okay. And I appreciate the correction. Now, the next part of the problem is about the net torque portion. So I'm just going to make this a little smaller to give us a little space and remind us that we're dealing with a statics problem, so net torque equals 0. And again, a series of steps here that I'm not going to write out, but are things you should think about. The first step is to decide if it's going to be a first or second law problem. We've done that. The very next step, before we go any further, is to identify what you're going to use as your fulcrum, or your axis of rotation. That really depends on the problem. So although step one is to identify the fulcrum or axis of rotation, in future problems, if you want these notes to apply in the future, you may be given a clear and obvious fulcrum that you should use. And in those cases, use it, especially if the object is going to rotate about that point. Use that fulcrum. If it is a net torque equals 0, you are free to pick where the fulcrum is. But there are some choices that are better than others. There are some choices that will make your problem easier to deal with than others. And there are some fulcrums that you can choose that can definitely make your problem harder. So when choosing where to put your fulcrum, be careful. One hint I will give, third thing to write down, is you can place the fulcrum at a force that is unknown. That will make that torque 0. Now that's effective in a lot of ways, but be careful. If you're trying to find out the value of that force, rendering it out of your equation is a bad idea. But like for us, we want to find both tensions. We know what the sum of both tensions is over here. So if we can find one, we can always find the other. You follow me? So I think for this problem, it would be best to place the tension at place the fulcrum at one of the tensions. So you pick, left or right. You guys agree terribly. So we'll place it there. Now, I will decide this. I'm going to say that out of the board is positive. So this is our point of rotation. So from our point of rotation, out of the board will be positive. Next, I would lay out all of the torques. We have potentially 4 torques. The torque from the left tension, the torque from the right tension, the torque from the meter stick, and the torque from the 500 gram mass. These are all of our torques. Now, if you're keeping notes, that step was lay out all of your torques. I would do it just like this. And you need to get 4 pieces of information for each torque. Each torque requires knowledge of the torque arm length, the applied force, the angle between the torque arm and the applied force, and whether that torque is positive or negative. 4 things: torque arm length, size of force, angle, and positivity and negativity. So the 4 things that you have to find for each torque. We're going to add them all up and set them equal to 0. So let's go through the process. The first one's easy. The distance from the pivot to tension L is 0. So this torque arm is 0. It just zeroes out that torque. So let's go to the next one. Now the next one is the weight of the meter. Well, the next one is TR if we do it in order here. So let's do TR. The torque arm length is from the pivot point to the point of application of the right tension. How far is it from 24 to 76?
50.
So 0.52 meters. I'm going to convert everything to meters because I know that the force meters that I'm using are in newtons. And so I want everything to be in units compatible with newtons. Next, I don't know the size of this force, so TR. Next, I have 2 students, maybe 3, who can verify if the tension is perpendicular to the meter stick. Would you guys verify it for me, since the 3 of you can see it? Is that okay? So I'm going to say sine of 90 degrees. Now, right-hand rule to determine positivity or negativity. We got the old right hand. Pivot point's here. Starting from the pivot point, I point along the torque arm towards the tension. And keeping my finger pointed that way, roll my wrist until my middle finger points in the direction of the tension, which is upwards. My thumb is now pointed into the board, or directed towards the front of the classroom. I said out of the board is positive, so this represents a negative torque. And that torque is attempting to pull the meter stick this way, right? It's pulling up on the meter stick, trying to get the meter stick to go this way. That makes sense. So this, from your vantage point, would be a clockwise torque. But I'm using my rules of positivity and negativity. That makes that a negative torque. Let's go to the meter stick. First, I need the distance from 76 centimeters to 50 centimeters. Thank you. Boy, these are not the hard questions, but I'm trying to find the size of the torque arm. The force we know to be 0.78 newtons. Or 0.76 newtons. It kept changing. Now, this is going to take my word on it. Does the meter stick look level? I tried to make it level. Does it look level? Because that's how we determine this angle. And now we have to go deal with positivity and negativity about that one. So I start at the pivot point towards the middle of the meter stick. That's my torque arm distance, but the force of gravity is downwards. My middle finger points downwards. So this must be a torque that is out of the board or towards the class, causing the meter stick to roll this way. Meaning if that was the only torque acting, it would cause the meter stick to pivot about this point in this direction. Good? So based on that, that's a positive torque. All right, last, our torque arm from the 40 centimeter mark to the 76 centimeter mark is how many centimeters? How many? 0.36 meters. We are hanging 4.9 newtons of force there, sine 90 degrees, and that torque is in the same direction as the weight, so that will be positive. Now, let's take a quick minute, work these out. We know this one's 0. This one is negative 0.52 TR. This one is 0.26 times 0.78, which is 0.2028. 0.2028 meter newtons. And 0.36 times 4.9 is 1.764 meter newtons. These have to sum to be equal to 0. So we've laid up all of our forces. We laid out all of our torques. We evaluated each torque to look for its torque arm length, force, angle, and positive or negative. We computed the torques we could, and now we're going to add them all up and set them equal to 0 because this is a statics problem, a first law problem. So negative 0.52 TR plus 0.2028 meter newtons plus 1.764 meter newtons equals 0. This appears to be one equation and one unknown. This is because we eliminated the one tension. Now, we could have chosen a different place to be our pivot point, but if we had, we'd have two unknowns here. We could still solve it because we'd have two equations with two unknowns, but you see why it makes it easier to eliminate one of your unknowns. So now we can find that out. I find that TR equals 3.78 newtons. Did you guys find that too? That's not it. We need both. So TL will be 5.68 minus 3.78. So TL is going to be 1.9, 1.897. I'm going to say 1.90. All right. Let's go over there and check the meters. So we're going to move the weight to somewhere over here. We don't know exactly where, but we know we will reach a point where it will become unstable. Well, that's no good. We're going to try and force, or at least find a place where the system becomes unstable. And we're going to do so by talking about moving the mass over to here someplace. So I don't know where we're going to move it. So we're changing the tenets of the problem a bit. This side isn't going to change. We are still hanging the same things. I don't know if we're going to use this pivot point or not, so we'll start that portion from scratch, but we know that this support is still at 76 centimeters. All of this is going to change because one of the tension, maybe not all of it, but we don't know where our pivot point's going to be. So I say we start this part from scratch too. Now we're still going to have 4 torques to work from, and we may or may not keep them all. One might zero out. We know what we're talking about here, but we're looking for a point of instability. So there, I think we go to this and we say, all right, we're going to start from here and see if we can't find out how to solve this problem. Now this problem introduces something a little bit different than before. In this problem, we don't know this distance r. We're trying to find it actually. So let's start. Where should we place the pivot point? See, I think our instinct would be to put it at TL because we know TL is going to be 0, but that's just it. We don't get to put in a value for 0 if we eliminate the variable. So I don't think we should put it at TL. Now, I think TR is a good choice because we don't need to know the value of TR. We're not asked for it. So eliminating it is fine. I would not put it here. Some people suggested putting it there, but if we put it there, it'll work. We'll be able to find our answer out. But every single torque arm is going to have R in it if we put it there. And that means that every one of those torque arms is going to have an unknown value. That's going to be a little bit more work. So as we try to be efficient, I think placing it here is probably your best bet. So let's reevaluate. Starting with TL. TL is 0.52 centimeters, 0.52 meters away from TR. We're still going to have the sine of 90 degrees working with us, but we do need to right-hand rule it to figure out whether it's positive or negative. I say we stay with out of the board as being positive. So coming over here, point towards TL from TR, roll my wrist upwards. Looks like that's a positive torque. So I'm going to treat that one as positive. All right, TR we've eliminated, so I don't have to work with that one. TM, we are 26 centimeters away from the center of the meter stick. And we know that that is a 0.78 newtons. Still sine of 90 degrees. Do I need to go over there and do the whole right-hand rule to realize this is in the opposite direction? It's going to have to be a negative torque? Good. I was hoping you'd say that. And let's do the 500 gram mass now. We don't know the torque arm length. It's R. We know the value of the force. It's 4.9 newtons. And still sine 90 degrees. This one we should do the right-hand rule for because it's kind of new. my pivot point is here, but the weight's gonna be placed over here someplace, right? So my pointer finger that way, and my force is already down, so it looks like this is gonna be a positive torque, causing this kind of motion, so positive torque. Alrighty. We have evaluated each of the torques. I'm sorry, we have found each of the values for each torque. Now it's our turn to evaluate them. So I'm going to have 0.52 TL, and let's see, 0.26 times 0.78 is going to be the same as before, 0.2028 meter newtons. And then I'm going to have 4.9 R. Oh, and this one's negative. It's not particularly clear, but kind of short on space. There we go. All right. Add them all up. 0.52 TL minus 0.2028 plus 4.9 R equals 0. Now, what was that condition? What's TL going to equal at the unstable point? 0. So we wipe that out, setting TL to 0. And now we can get an expression for R. I get 0.04. 14 meters. Now, this should be the tipping point. Let's see if it is. A boom arm problem has usually an attachment point of some sort, a pole or a wall or something. A boom is just a pole of some sort. If you sail, you'll know that one of the sails will have a boom on it. You can swing the boom from one side to the other side, or swing the jig from one side to the other side. It allows you to tack against the wind. But generally, a boom arm is used for supporting something. So you might have a cable of some sort that attaches to the boom arm, and then, say, you hang a storefront sign from the arm. There are configurations that are more stable and put less pressure on the cable and on the boom. And those are questions that I think are kind of our next ones to look at. Of course, looking more into the future, this is a torque problem. All right. One of the more critical kind of problems that I like to make sure we look at is one that will probably face many of you sometime in the future. Anybody ever have to climb on one of these? I do it all the time. But yeah, ladders not only have weight limits, but they are clear about where you can and where you should not step. Now, most of the time where you do not step is related to it being unsteady due to a high center of mass. But you need to have adequate friction here, right? You can probably imagine why. And the angle that the ladder makes here, also critical. The angle gets too shallow and you have a tendency to fall over backwards. That's why there's, on almost every ladder, a level that's mounted a little bit funny, because you're supposed to level the ladder to that orientation that provides you with the most stable position for climbing up the ladder. But do you see how this is a torque problem? We have a collection of forces acting on the ladder, but also there are torques acting on the ladder. So this is a torque problem in the same way.